Hello everybody, I'm Michelle. I'm a licensed massage therapist from Washington, and I bring you MBLEx study resources here on YouTube, lots of videos on all the topics that are very important to that exam. And also on my website, there's a link in the description below, and it's in the description and it's also in the pinned comment that has a huge list of all the resources that I have, ebooks, study guides, practice tests, and courses. Full courses to help you prepare for the massage and bodywork licensing exam with calm and confidence. Right now, I'm creating another course. It's a big mega course. It's a big deal to me, and it is anatomy and physiology for body workers. As I create each video, I'm posting them for you so that you guys can have early access to this information. Right now, we're in the section on the nervous system, and we're going to close out all of the technical information about the nervous system, talking about nerve impulses and neuronal pathways. All this week I've been talking about the nervous system. Tomorrow we're going to be talking about the cranial and spinal nerves and the nerve plexi and why those are important. But today it's all about those nerve impulses and how they work. So we're going to talk about the action potential. We're going to be talking about synaptic transmission. We're going to be talking about reflex arcs and neuronal pools and circuits. And then at the very end, we're going to be talking about the MBLEx practice, or we're going to be going over MBLEx practice questions. Excuse me while I scratch my nose. This is a very technical video. So, I mean, we're imagining how these transmissions happen going from our central nervous system to the peripheral nervous system and back. We're imagining it on such a microscopic level, and it's extremely tedious. And I know that this video is not going to be popular, but it is something that you do need to know for the MBLEx just in case. Conceptually, it really helps. All right, and it helps you to be able to understand also why ions make such an impact on the way that those impulses work. So go ahead and watch the whole video. Just listen to it. Just absorb the information. Don't worry about memorizing it all. But if you have a fundamental understanding of these concepts and a question comes up in the MBLEx about it, you can pick the question apart and take the information that you do have and you could come really close to answering that correctly. So let's go ahead and get started. So, how nerve impulses travel and connect different parts of the body. So the nervous system is powered by an incredible communication network that transmits messages faster than any other system in the body. Every movement, sensation, and reflex begins with an electrical impulse traveling along a neuron, crossing synapses, and activating intricate pathways that connect the brain, the spinal cord, and the body. Understanding how action potentials, synaptic transmission, and reflex arcs work gives massage therapists and body workers insight into how the body responds to touch, pain, and relaxation, helping them to support the client's nervous system balance and recovery through intentional body work. Okay, so definitions for nerve impulses. A nerve impulse is an electrochemical signal between the central nervous system and the peripheral nervous system. It can be simple with one sensory or motor neuron running from the spinal cord to the effector, which is the thing that is trying to, let's say with the motor neuron, it would be the organ, muscle, gland, and with the sensory, it would be one neuron going from the place where you felt it to the central nervous system, either the spinal cord or the brain. Or it can be complex when it comes to conscious thought processes and activities. So there can be multiple neurons firing to each other and creating these cascades. So first thing we want to talk about is the action potential, which is the electrical impulse that runs from the cell body down the length. And we're going to talk about that more in detail. So electrical impulses are measured in millivolts. So it's an actual piece of little tiny bit of electricity that gets charged in this process. Ions are the molecules that make it happen. that make that happen. They have a positive or negative charge depending on how many electrons they're missing, right? So if they're missing electrons, then that means that they have a negative charge. If they have too many electrons, they have a positive charge. And they live in and around the cell membrane of a neuron. A neuron has the same kind of composition as any other cell, in that it has a membrane barrier that is hydrophilic, right? So it keeps a particular charge around it to keep water close and to keep everything else far away. Okay, so more definitions here. Let's pretend these are all the cell membranes, and this is the way that those ions can pass back and forth. There are 3 different ways that they can pass back and forth over that cell membrane. We have the ion channel, where they pass through a channel that can open because of a stimulus, or close when a stimulus tells it to close. Then there's the ion pump, which uses ATP to transfer ions when there is when it's going against the charge, right? You have too much charge of one thing and you still want to get more charge in there, then you have a pump for that to make it happen. It uses ATP because it goes against the flow. And then there's diffusion, when you have less of an ion on one side and more of an ion on another, and it just goes right through the membrane to spread it all out so it's even. Come back to threshold stimulus in a second. So there are the sodium and potassium ions in the neuron are going to travel back and forth inside of the cell and down the length of the axon of a neuron, which creates the triggering response. But there has to be a stimulus that gets to a certain point to make those pathways open, because naturally there is a specific balance of sodium and potassium ions, and I'm going to show you that in a second. But there has to be a stimulus that causes the cascade of an inactive membrane to start moving these ions back and forth. So the stimulus gets to a point and it causes a cascade. So let's take some more information here. Here's the cell body of a neuron, here's the axon, here's the synapse. So the cell body creates a threshold stimulus that gets to a certain point, and at that axon hillock, the trigger happens. And it's like sparkle, 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 all the way down the end of the axon, and psh, the synapses fire. Okay, so this just gives you a big visual of how it happens from the cell, and then psh, the domino effect of sparkles all the way down. So we're going to go into detail about that. So definition specifically of action potential is when the body generates an electrical impulse at the base of the axon, also known as the hillock, triggering a chain reaction running down the length of the axon. Okay, I think you guys got the picture. But let's talk about exactly how that happens, and just listen, just absorb the information, and it will be with you forever. Maybe all the details won't be there, but you will understand the fundamentals of how it works. So naturally, in a neutral, we call it neutral, but it's polarized. In a neuron cell that is not doing anything, you have way more potassiums in the axons, and you have way more sodiums on the outside of the cell membrane of the axon. So naturally it is polarized, so there's more positive on the outside and there's more negative on the inside, because there is more charge of sodium, more electrical positive charge of sodium on the outside. So they call that polarized. Its neutral state is polarized. So that's neutral. That's how it is when it's not doing anything. But the threshold stimulus is reached in the axon because the cell started the chain, okay? And it opens that ion channel to pour those sodium ions in. So sodium ions come in. That changes the ionic composition inside the cell membrane to be neutral. and they call that depolarization. There it is. It becomes neutral inside. For a second, nothing happens. And so because of that, they call it the refractory period. It prevents the ionic exchange from going backward, back toward the cell body. It forces it to only go in one direction because we have this refractory period where nothing happens. The potassium diffuses back out because it wants to be in a situation where it's polarized. It wants to be polarized. So it pushes it, it goes back out, which forces more sodium in, and it just goes down the chain in the direction from the cell body down the axon to the synapse. It's one direction because of this refractory period, this gap that prevents it from going backwards. Repolarization is the name for when the potassium goes back out and creates another overly positive environment inside of the axon. So those are three terms that are important to know for how the action potential carries out. Okay, so that's the story in an unmyelinated axon. It doesn't have any of the lipid sheath to insulate it from an electrical signal. Now in a myelinated axon, they get to skip the areas where the insulation is. So the charge goes skip, 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 skip down the length of the axon. These are Schwann cells in the peripheral nervous system. And so that's how the action potential works faster. Myelinated axons pass their electrical charge for action to happen faster than unmyelinated. So that's why it's important for us to have our axons myelinated, is because our impulses happen faster. And just one more thing I wanted to say about the refractory period is it's like such a tiny fraction of a moment that refractory period happens. And it's only significant in that it prevents the charge from, the change in charge from backtracking. Okay, so moving on to, that's how action happens going from the cell body down the axon. And then it goes down to the end of the axon where the synapse is. The synapse is the place at the very end of the axon where the synaptic bulb is the very end of it, the tippy tip, connects with another structure, whether that be another neuron, or whether that be the organ or the structure that the motor response is trying to connect with. So the synaptic bulb is the very tip of the axon, and there can be like a spray of them, right? And when the action potential happens, it triggers neurotransmitters to come out of that synaptic bulb, and those neurotransmitters start the ball rolling with the other end, or if there's leftovers, then they get reabsorbed, or there's some enzymes that eat them up, or they go back. Yeah, they go back, or they just get absorbed into the body. So yeah, those neurotransmitters come out and they create the thing that happens. So there we go. Synapses. A synapse is the whole thing, the whole connection. That includes the effector or neuron, the gluteal cleft, come on now, synaptic cleft, and the synapse or the synaptic bulb. So the synapse is everything, the synaptic bulb is the tip of the axon, the cleft is the gap, and then there's the effector. Yeah, neurotransmitters is the sprinkle that comes out of the very tip of the axon that's triggered to come out because of that action potential. Some neurotransmitters that you might know about are acetylcholine, which triggers a muscle contraction. Norepinephrine, dopamine, serotonin, and endorphins are all neurotransmitters that help give you certain sensations, right? So when there is a connection between two neurons, we have a pre-synaptic neuron and we have a post-synaptic neuron. Okay, so there's the information comes down and the action potential synapse is triggered, and that's in the presynaptic neuron, and then the postsynaptic neuron, they get the information and they do something else. Okay, so I guess we're moving on now. We're going to talk about reflex arcs. So that's just in general. So the synaptic transmission is just in general how the action potential happens, how the neurotransmitters come out, and how the information is conveyed. And then for the neuronal pathways, we have reflex arcs, which is where the information comes up, goes into only the spinal cord, and the motor, there's an interneuron that makes a decision about what to do, and the motor neuron makes the change happen. So a reflex arc is a predictable motor outcome for specific stimulus. The interneuron has a program. This is what we do when this stimulus happens. And those are created when we're babies or over time. So things become reflexive, what we call motor memory. That's all coming from the spinal cord. So in the gray matter of the spinal cord is where the interneurons live. The information, oh, that's a hot pot, comes up into the dorsal nerve root of the spinal cord. And then there is a synapse that hits that interneuron. The interneuron makes a decision. Synapse gives an order to the motor neuron, which goes out and says, move that freaking hand. Efferent, remember, is the motor part. Afferent is the sensory part. So here's an afferent nerve impulse. And then going back down, that's an efferent. All right, and then we remember the difference between dorsal and ventral. That's how a reflex arc happens. So some are very simple and some are more complex and require more interneurons. Yeah. And then the last thing that we need to understand is how these neuronal pathways converge or diverge from each other. That's over here, this area. So that's how they communicate, is there's a synapse between these sets. So inside the axon, there's a split, and then the information goes out. That would be much more for a motor neuron pathway. So it starts from the central nervous system and it splits. And then the convergence typically is the sensory information, comes from all kinds of different areas, and it comes up and converges into one cell body. And those are two terms that you need to know. And this happens when the next video, I'm going to be talking about the cranial and spinal nerves and how they split off from each other, split off and come together. And that's all because of these motor and sensory divergences and convergences. Last thing I want to talk about is that, and it's just a term you need to know, is neuronal pools, and that's where the interneurons are organized into functional groups. As our body, we're born with some inherent neuronal pools for helping us with our basic survival, but then as we're growing up from babies and we're learning certain things, we develop more neuronal pools that make these connections happen, so that that's part of our neuroplasticity, is that these interneurons collect in increasingly complex ways to help us to do complex tasks. Specifically for memory, they can inhibit or excite each other. So like you can remember something when you're working on one thing, another part of your brain lights up because you're remembering something. That's one neuronal pool exciting another one. So there's a great example. I think that's it. Yep, we're going into the MBLEx questions. So that's all you need to know about those topics. I wanted to keep it short and sweet because it was very abstract. And there was a lot of terminology for you to remember. But thanks for hanging in there. Let's get these MBLEx questions done, and so that we can move on with our lives, right? So first question, which event directly triggers the generation of an action potential in a neuron? What happens to start the action potential? Getting started. Okay, so let's look at our choices here. A, potassium ions rapidly entering the neuron, causing repolarization. Now from what I remember, our potassium ions naturally live inside of the neuron or in the axon of the neuron, and when they diffuse out, it's called repolarization. So that's not true. B, sodium ions rushing into the neuron after a threshold is reached, causing depolarization. B looks like a good one. C, neurotransmitters binding to receptor sites in the postsynaptic membrane. So this is something that actually happens. The postsynaptic membrane is something that actually happens, but that's not a part of the action potential. And then D, the sodium-potassium pump restoring resting membrane potential. I don't think there's a sodium-potassium pump involved in this part. It does. The sodium-potassium pump is something that exists, and it does restore resting membrane potential. That is a thing, but it's not part of the action potential mechanism. So I'm going to go with sodium ions rushing into the neuron because a channel was opened. So B, sodium ions rushing in is the correct answer. An action potential begins when the neuron reaches its threshold, prompting voltage-gated sodium channels to open. The rapid influx of sodium ions causes depolarization, making the inside of the neuron temporarily positive relative to the outside. Repolarization follows as potassium exits the cell to restore resting potential. Okay. So next question. Which of the following statements about the action potential is false? So which is false about? So that means we have 3 true questions and 1 false question. Okay. About action potential. A, it occurs when a neuron's membrane potential reaches threshold and sodium channels open. Okay, let's see, is that true? About action potential. It occurs when a neuron's membrane potential reaches a threshold and sodium channels open. Okay, that's true. Okay, so B, it travels in one direction along the axon due to the refractory period. That's true. C, it requires continuous input of neurotransmitters to keep propagating. No. I'm going to talk about that in a second. It involves rapid depolarization followed by repolarization. That's true. So C, being wrong, I think it's wrong because the action potential runs down the axon because of the depolarization and repolarization of the ions, which triggers the neurotransmitters to come out at the synapse at the very end of the axon. Okay, so let's see the explanation. An action potential is a self-propagating electrical signal triggered when a threshold is reached, causing a sodium influx, which is depolarization, followed by a potassium efflux, which is repolarization. The refractory period ensures one-way travel along the axon. Once initiated, the impulse continues automatically. It does not require ongoing neurotransmitter input. Next question. Which statement correctly describes what occurs at a synapse? Remember, the synapse is the place where the axon connects with another structure to create something to happen. So A, the action potential jumps directly from one neuron to the next through physical contact. We're looking for the correct description. Action potential jumps directly from one neuron to the next? No. It happens because neurotransmitters are released. So B, neurotransmitters are released from the axon terminal into the synaptic cleft and bind to receptors in the postsynaptic cell. True. Okay. C, the postsynaptic neuron generates its own action potential before the neurotransmitters are released. No, it needs the neurotransmitters for that to happen. And then D, the signal is transmitted by the myelin sheath bridging the 2 neurons. That's not something that happens. So let's see. B would be the correct answer. And let's see the explanation. A synapse is a tiny gap between the neurons where communication occurs chemically. When a nerve impulse reaches the axon terminal, neurotransmitters are released into the synaptic cleft and bind to receptors on the postsynaptic membrane, allowing the signal to continue. The neurons do not physically touch, and myelin does not bridge the synapse. Last question. Which of the following best describes a reflex arc? Remember, reflexes happen in the spinal cord. A, direct connection between the brain and skeletal muscles for voluntary control. No. B, a simple automatic pathway involving a sensory neuron, an interneuron, and a motor neuron. That looks good. C, a feedback loop that requires conscious awareness before responding to stimuli. No. Conscious awareness? No. That's not part of a reflex. A process that only occurs when both sympathetic and parasympathetic neurons are activated. That's not a thing. Okay, so B is a simple automatic pathway involving a sensory neuron, an interneuron, and a motor neuron. A reflex arc is the basic functional pathway of the nervous system that allows for automatic, involuntary responses to stimuli. It typically includes a sensory receptor, sensory neuron, interneuron in the spinal cord, motor neuron, and a motor effector, like a muscle or a gland. Reflexes do not require input from the brain before the response occurs. All right, that's it for us. Be sure to get the PDF of the slideshow so that you can refer to this information without having to get on the video again, unless you want to just listen over and over again. I like doing that too. Make sure and subscribe so that you're aware of more videos when they come out. And also be sure to like the video so other people who are MBLEx students can have access to this information in the future. All right, see y'all in the next video. Toodaloo.